The James Webb Space Telescope is revealing the universe like never before. Our planets, the furthest galaxies, and the strangest phenomena. What you can see is actually material falling into a black hole, and that's only in the first few weeks. There's going to be a lot more discoveries to come. The James Webb Space Telescope is a product of decades of hard work from scientists around the world. I have been waiting my entire astronomy career for JWST. It is absolutely revolutionary compared to what was available. It's very, very rare in science that you make a big step forward in your measurement capability in the way that JWST has done for astronomy. It just doesn't happen very often in the history of science, and that's really exciting and significant. One of the things that makes James Webb so special is its gigantic mirror. There are various things that make the primary mirror on James Webb special and incredible. The first is the sheer size of the mirror. It's the largest one ever launched. The Webb mirror is around 6.5 meters in size. If you can imagine that, it's bigger than most houses you're walking by. It's so large it wouldn't fit in the rocket, so they had to devise a way of folding it up so that it would fit inside the top of the rocket. It's absolutely humongous, and that makes a really big difference in terms of the sensitivity of the telescope. It's thousands of times more sensitive than Hubble, a step forward of factors of 1,000 or more, in fact, several thousand. The bigger the mirror, the more light you collect, the bigger the collecting area, the more sensitive you are, and the further you can see. The other thing that makes it absolutely incredible is the precision with which it's been made. If the mirror were stretched to be the size of the United States and you were to measure the biggest bumps and dips, you would only be looking at a bump or a dip of about 1 centimeter. It's absolutely incredible, and that's what generates near-perfect images from the primary mirror. But it's not just the mirror that makes the images from James Webb so incredible. It's also the type of light that it detects. The James Webb Space Telescope detects infrared light, a wavelength of light that we can't see. But the unique properties of infrared make it incredible for exploration. With infrared light, you can see the atmospheres of exoplanets. There are molecules in star formation regions, things like caffeine, alcohol, and water ice, the signatures of life around other planets. So, just a few examples. Infrared opens up enormous possibilities for astronomers like Olivia and allows them to capture images that would have been impossible in the optical range. Even within the infrared spectrum, there are multiple different wavelengths on board Webb. There are 3 instruments that observe near-infrared, which is closer to the visible spectrum. But the instrument garnering the world's attention is the mid-infrared instrument on board JWST, known as MIRI. MIRI is essential for JWST. Without it, you can't see the cooler phenomena in the universe. You can't peer back into the earlier stages of star formation as you would like. MIRI is an incredibly significant and important instrument. The images it captures contain far more detail than ever before. When we look at the universe in this new wave of light, we find things that we hadn't expected. And that's a critical part of discovering new aspects of the cosmos. MIRI allows us to see further along the infrared spectrum, which in turn lets us see through dust clouds and further back in time than ever before. This is because as galaxies move away from us, the color they emit shifts further into the infrared. The longer the wavelength we can observe, the further back in time we can see. Despite its importance, MIRI very nearly didn't make it on board James Webb. MIRI wasn't initially part of the plans because it seemed technically very complicated, and early thinking about the science was slightly different. I started making the case that a mid-infrared facility was truly needed on the telescope. Gillian Wright, the European principal investigator for MIRI and director of the UK Astronomy Technology Centre, was instrumental in pitching to get MIRI on board. When I found out it was confirmed, I remember being very happy, and also knowing I was about to be very busy for many years. Construction of the James Webb Space Telescope began in 2004, and 17 years later, on Christmas Day 2021, with MIRI securely on board, the telescope finally launched, lifting off from a tropical rainforest to the edge of time itself. James Webb began its voyage back to the birth of the universe.
I had been looking forward to the launch for many years, and as Christmas Day approached, I was extremely nervous. I don't think my family enjoyed Christmas morning with me because I had the TV on, watching the launch. I had my pillows ready in case I needed to hide, but everything went perfectly. It was an incredible launch, a real pleasure to watch, a wonderful Christmas present. Over the next few months, the James Webb Space Telescope traveled more than 1.5 million kilometers from Earth to its new home, gradually turning on its instruments along the way. It was both exciting and nerve-wracking, because after decades of work, you never know if something might have gone wrong. Once the instruments were operational, it wasn't long before the first images started coming in. I knew they would be spectacular, but what I hadn't prepared for was just how spectacular they actually were. The first images were breathtaking, absolutely stunning, and I've been smiling ever since. It was almost emotional. The images are spectacular, and the discoveries within them are even more remarkable. One of the most exciting aspects of the early images is how MIRI adds information. I can see details I knew existed, but never thought I'd be able to observe with a scientific instrument. Some of the first Webb images released were of the Southern Ring Nebula, a planetary nebula representing a star at the very end of its life. In the MIRI images, we actually see a second star, a red star and a white star, a binary system. This was the very first time we've observed this binary companion in the Southern Ring Nebula. An image of Stephan's quintet shows 5 galaxies interacting with each other. What you can see in this galaxy up here is actually material falling into a black hole in an active galactic nucleus. The material in the galaxy is orbiting and falling into the galaxy itself. This is 13 times further than what we've been able to see before in the infrared. JWST has already found the furthest galaxies we've ever seen. The highest redshift ones, the closest. And that's only in the first few weeks of operation, which is really exciting. I think it's an indication that there are going to be many more discoveries to come with Webb. We designed it to answer many of the questions we already have about the universe, but, as with all new telescopes, there's a realm of new discoveries, mysteries that will arise. I think it's really exciting to encounter new questions we don't yet know how to ask. Seeing something that not only has nobody ever seen before, but nobody expected to see, is incredible. I feel very privileged to be part of this. I'm proud to be part of JWST. It's been an amazing journey and a fantastic privilege. When I see these images, I'm just full of smiles. The very first data we got from NIRCam, for maybe 15 minutes, we thought something was wrong with the instrument, only to realize that the instrument was working perfectly. What we were seeing was physics. Physics we had not seen before. The Sun is the most important celestial body in space, at least to us here on Earth. It drives weather, ocean currents, seasons, and climate. Without the Sun's heat and light, life on Earth would not exist. But we don't understand it as well as one might think. That's where Parker Solar Probe comes in, NASA's first ever mission to touch the Sun. It's a voyage of discovery, a groundbreaking mission steeped in history. This is Nicola Fox, the Director of Heliophysics at NASA. The concept of Parker Solar Probe has been around for over 60 years. It's been the most high-priority science for us to do, but it was always so challenging technically. Finally, technology caught up with the scientists' dreams, and we were able to achieve the mission. Nothing about Parker Solar Probe was easy. Not only has the probe traveled nearly 90 million miles closer to the Sun than Earth, but it's also had to withstand temperatures over 1,400 degrees Celsius. Keeping it cool is the job of thermal engineer Betsy Conn. How hard could it be, she asks. Designing a heat shield for something going to the sun is an immense task. Anytime you attempt something that has never been done before, it's exciting but stressful. One principle in space engineering is to keep things simple. The Parker heat shield is about 4.5 inches thick, just 4.5 inches, protecting the probe from thousands of degrees Celsius. On both sides is a material called carbon-carbon. Similar to the graphite epoxy found in golf clubs or tennis rackets, in between is carbon foam, forming a big sandwich that protects the probe from the sun. As Parker Solar Probe approaches its closest approach, the front side of the heat shield will reach 1,400 degrees Celsius, while the spacecraft, where all the electronics are, will remain at room temperature, around the 20 degrees Celsius. It's almost as if the probe doesn't even know it's at the sun, yet it can carry out amazing science. Thanks to Betsy and her team, Parker Solar Probe will travel closer to the sun than anything before, while remaining roughly at the temperature of an average swimming pool. One more detail made this historic moment nerve-wracking for the scientists. Parker Solar Probe is fully automated. Once the probe was fired into space, the scientists could not control it. There are sensors called solar limb sensors that stick out behind the heat shield. If they light up, the spacecraft knows it's off track and corrects itself automatically, without any commands from Earth. On August 12, 2018, after over 60 years of planning, Parker Solar Probe finally launched. I kept all your original details and phrasing, but made it flow more smoothly, fixed some repetitions, and slightly polished sentence structure, so it reads like a continuous story. If you want, I can also turn this into a version optimized for a long-form video script, keeping every line timed for narration and visuals, so it's ready for voiceover and animation. Launched by every single member of the Parker Solar Probe team. You know, when we watched the launch, it really felt like we were losing a member of the team. I worked on Parker Solar Probe for 10 years, and at launch, I cried. It was a very emotional moment, and even now, when I see the launch videos, I still get emotional about it. There was a sense of separation anxiety, the feeling that this thing we had worked on for so long was going to leave and not come back. She is the part of the team that's actually doing the exploration. Parker Solar Probe had one extra helper out in space though: Venus. Rather than flying in a straight line toward the sun, Parker Solar Probe uses the gravity of Venus as a giant slingshot, catapulting it into closer and closer orbits of the sun. The first Venus flyby, I think, was the really key one for everybody. Once that maneuver was done, we would go for the sun at that point. The first solar pass was really emotional but amazing, of course. When it was actually in the solar pass, that's when the terror hit. We can't actually talk to the probe while it's going in. So, until the spacecraft came back out from the other side of the sun and everything was healthy, it was nerve-wracking. When you get that green beacon, knowing that everything is looking good after a solar pass, it is just an amazing feeling. My God, we've done it. After having launched Parker toward the sun on its 8th flyby in April of 2021, Parker Solar Probe finally entered the atmosphere of the sun. It reminds me of 1969 every time I see the movie when Neil Armstrong touches the surface of the moon. One small step for man. That was monumental in a way. It's a parallel to Parker Solar Probe. When you fly through the solar corona for the very first time, nobody has done that before. It was so exciting and humbling to have launched this mission basically toward the sun and receive data that no one has ever seen before. Just eye-opening. Noor Rui has been working on Parker Solar Probe for over 14 years. In case you're wondering if he still enjoys it, it gets better by the day. But the thing that's been most exciting, more than anything before, is the incredible discoveries coming from Parker Solar Probe. The amount of discoveries is way beyond any of us could have imagined. It's just mind-boggling. Every day, we are discovering new phenomena in the data that Parker Solar Probe is sending us. The very first data we got from the field's instrument, when we were looking at the magnetic field measurements for maybe 15 minutes, we thought there was something wrong with the instrument, only to realize that the instrument was working perfectly. What we were seeing was physics we had not seen before. The switchbacks, basically, are where the magnetic field flips over itself, making a rotation of 180 degrees and back again in a matter of seconds to minutes. It is just fascinating. What is really important about these switchbacks is that they carry a lot of energy with them. That energy will dissipate into the solar wind in the form of heat and speed. 2 of the 3 goals of the mission are to explain coronal heating and the acceleration of the solar wind. So, the switchbacks could be the smoking gun that leads us to the answer to those questions. By understanding switchbacks, we could unlock the secrets of solar wind and how it's formed and accelerated toward Earth. Solar wind is not trivial. It reaches speeds of over 1 million miles per hour, traveling way beyond Pluto, and it affects our everyday lives. In 1989, a large solar flare caused the entire grid of Quebec, Canada, to fail, leaving them without power for over 12 hours. Think what it could do to a rocket or a satellite. As well as solving mysteries, Parker Solar Probe is also creating puzzles for Noor and his team to try and solve. Like any other mission, it answers questions, but by answering one question, it actually poses many more. That, in a way, is the essence of exploration. We come to this world as explorers, and we leave it as explorers. On the eve of Christmas 2024, we will reach the closest approach to the Sun ever. At 3.8 million miles from the solar surface, it's so close. After that, we do 2 more orbits, and that will be the end of the Prime mission. Even after this mission ends, the discoveries made during this epic mission will live on forever, in science and in the scientists. It is the highlight of my career, and it will remain the highlight of my career. Definitely being involved in Parker Solar Probe is an honor. We are really explorers, rewriting the textbooks about the Sun, and it's amazing to have played a small part in that. I am incredibly proud to have been part of the Parker Solar Probe mission. Parua Probe changed me forever. Parua Probe is an enabler in many respects. It, EMB, bolden us now to go after very challenging ideas and concepts for future missions. So we are not stopping here right now. The 2 Voyager spacecrafts are hustling through interstellar space at 35 million miles per hour. The space is so far away that it took 35 years to get there, and now we need new signs to understand it. I couldn't believe how nature was fooling us. It made us rethink everything we knew about the shape of our solar system. I think I discovered that the tail has a Quran shape, and even where the edge of our solar system actually is, there was a lot of confusion. Actually, the confusion lasted almost a year. Even just to understand what Voyager is trying to say requires a very special set of skills. It's really like a SS watchmaker. It needs to be a trained eye to tell me, can I trust this data or not? What's even more extraordinary is how Voyager, the old spacecraft from 1977 with 64 KOB of memory, was able to make this journey at all 321. We have ignition and we have liftoff. Both Voyager 1 and Voyager 2 were launched in 1977, and it had to be then. thanks to an extremely rare planetary alignment. It happens once every 175 years, where we could fly past Jupiter, get a gravity kick, and go to Saturn, get a gravity kick, and get to Uranus, and another gravity kick, and go past Neptune. Within just 2 years, Voyager 1 had reached Jupiter. Voyager showed us a planet which looks so serene through a telescope was actually rocked by hundreds of raging hurricanes, a glowing aurora at the North Pole, and 3 thin rings. Voyager took 33,000 images of Jupiter and its major moons that captured the world, and we'd get to see these pictures and go, "Whoa, look at that, what's this, what's going on?" It was music fantastic, and a night like tonight, our eyes, our minds, our souls, our blood are moving out through the universe. We're part of history, and that means that we have to replace the old myths with new ones. Just 1 year later, and Voyager 1 had already sped past Saturn, spying intricate details in the planet's rings. From Earth, scientists could only see 5 or 6 Saturn's rings. Voyager showed us that there were more than 100. And I can remember those first pictures as we flew away, looking back at that system and seeing the reflected sunlight in that structured ring system was just so beautiful. Then the Voyagers parted ways. Voyager 1 headed straight for the edge of our solar system. Voyager 2 took a more scenic route, reaching Uranus in 1986, and eventually Neptune in 1989, showing us yet more outstanding views of the green and blue planets, and spotted gas on Neptune's large moon Triton. And that was the main mission, the first human-made object to reach the distant world of our solar system. But the Voyagers weren't done yet. They were about to embark on the journey to search for the edge of our solar system. And before they left, there was one last thing to do. Convince NASA to turn the cameras towards Earth and take that very famous picture, the pale blue dot. On that blue dot, that's where everyone you know and everyone you ever heard of, and every human being who ever lived out there lives. It's a very small stage in a great cosmic arena. These images were the last of 67,000 images taken by the 2 Voyager spacecrafts. Their cameras were then turned off to save power as they carried on their journey towards interstellar space. The boundary where our sun's solar wind ends and the rest of our universe begins. Problem was nobody actually knew where it really was. Scientists thought that sooner or later, the charged particles that create solar wind were going to run out, and Voyager would enter a pristine environment of interstellar space. We thought that would happen, maybe just beyond Neptune. But no, that didn't happen. Well, we said to NASA, give us a bit more money, another 5 years. Well, this kept happening year after year. NASA, please give us a little bit more money, a little bit longer. We'll be there, as Voyagers 1 and 2 continued to move out into the outer reaches of the solar system. They remarkably continue to send very faint signals back to Earth. And this what makes it so interesting and so fragile. The whole instrumentation of Voyager was designed to visit the outer planets that have very strong magnetic fields. So now, we are dealing with a signal that is almost at the noise of the instrument. And because Voyager was not designed for that, it's miracle fit that all this steam is able to go mine the data and pull out the signal and tell us what's going on. Just 5 instruments were still operating on the spacecraft, and in 2012, more than 35 years since Voyager 1 left Earth, scientists started to see the first signs that they were crossing into interstellar space through the boundary known as the helops. Think about the helops as your walls of your house. This is what separates environment that is dominated by the solar wind from environment that is dominated from other winds from other stars outside of our bubble, the heliosphere. The expectation was that there would be a sudden shock, a burst of activity that would make it obvious we'd finally reached this sharp boundary. But the reality was much stranger. All of the detectors on Voyager were seeing particles suddenly appear and then disappear, then appear and then disappear, and nobody had a clue why these strange particles seemed to be coming from elsewhere in the galaxy. Gaily, did we cross or not? The data was so confusing. On one hand, Voyager was still being affected by the sun's magnetic field, but the particles were suggesting we had crossed, and turns out what really tipped the scale in the team was the radio data. The data was stored on the spacecraft using a tape recorder, so ancient technology, it's extraordinary, but it worked. And the data were gathered and sent back bit by bit. And 6 months later, we turned to the radio station of Voyager. And guess what? We heard these plasma waves converted into sound that we can hear, with the final proof that we had crossed the boundary into interstellar space. The first human-made object to venture into interstellar space. Even more extraordinary than crossing the boundary into interstellar space was what the data said about the shape of the solar system. I was tasked to create a computer model with all the physics that we know to kind of predict this shape of the heliosphere. It turned out that the solar system's heliosphere is not round like you think, but has a tail from whizzing around the galaxy. And more than that, I was finding that has a CO-sun shape, 2 horns with a void in the middle, with just a shock to realize that something such basic as the shape of our home is completely different. And all of this was discovered by a small, extremely low-tech probe, more than 10 billion miles away, and they're still going in 2018. NASA's Voyager 2 spacecraft crossed the boundary. Finally, both Voyager spacecrafts with their 1970s technology had reached where no human-made object had ever been before. Interstellar space, there's very little material. Very empty space can be very, very empty. The environment out there is colder and denser. And of course, it's dark. There's not a lot of light. You're far away from. The Sun Voyager has also discovered that our solar system's impact is much bigger than we thought. Before, we would have liked to get to a region where the heliosphere doesn't influence anymore. The interstellar medium, what we call a pristine interstellar medium. What we're measuring now is a medium highly disturbed by the sun. The Voyagers are still sending us ever fainter signals, still teaching us new things about interstellar space, but they're running out of time. We probably have 2, 3, maybe 4 more years of power to communicate with Voyager, but there are still so many mysteries left to be solved. What is the environment outside? What's happening? The nearby stars that are influencing our system, and so on. So one of the beauties of the Voyager mission, that it started as a planetary mission, gave us the first images of our planets, discover volcanoes in the solar system, and then it's went to discover our heliosphere, our vast, regions of our solar system, and enter into the galaxy long after their power has gone. The Voyagers will continue to rush away from us, monuments to human endeavor and exploration, heading out towards the stars. Voyager will continue its little journey in the interstellar space, way past when we, maybe as a species, will cease to exist, when we might move to a different planet. It'll keep going and going and going and going and going forever. Music. We used to seeing NASA fire up its rockets and launch billions of dollars of equipment into space. But what happens when it messes up? The Hubble Space Telescope project has suffered yet another setback. And how do you fix a billion-dollar mistake up in space. I did not have a line item that says, NASA put wrong mirror in telescope, with engineers needing to fix it not once, but twice. So the summer 2021 event was a pretty intense anomaly. This is a story of how the Hubble Space Telescope nearly destroyed NASA's reputation, and the retired engineer that helped bring the telescope back from the brink. Both times when I received the call, I was honored that they would think of me to try and help them resolve this. This is electrical engineer Ron Barish. I started working on Hubble in 1987. Approximately 2 years before launch, Hubble was one of the most ambitious space projects the world had ever seen. NASA had spent hundreds of millions designing a massive mirror in the telescope to get the sharpest pictures of the universe ever seen. Expectations were high. It promised to catapult space science into a radical new era, and all eyes were on it and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe. It was very exciting to watch the launch when it was turned on in orbit. Very exciting. NASA was quick to champion it as the greatest advance in astronomy since Galileo, but then disaster struck. The Hubble Space Telescope project has suffered yet another setback. Engineers have discovered that the giant telescope has a warped mirror, which means the images sent back to NASA are distorted. The pictures are little better than those from ground-based telescopes. We found out that there was distortion in the image. The images I saw were blurry. They called it spherical aberration. When light enters the telescope, it's reflected first by a large 8-foot mirror onto a smaller secondary mirror, which concentrates the light onto the cameras. If either the mirror is slightly out of true, the picture becomes distorted, and that's exactly what had happened. The mirror hadn't been tested. With the rest of Hubble, had it been tested, the scientists would have seen that the mirror was ground incorrectly by just 150 thousandths of a human hair, tiny but enough to ruin everything. Everyone on the project was very disappointed. And it was an embarrassment that we had spent so much time on the program, and that there was a significant flaw. The news was not very kind to the project. Well, the American taxpayer, they're not going to be happy. Well, look, you launched this $2 billion white elephant. What are you going to do? And the bad news kept coming as NASA's reputation received blow after blow after blow. But despite the setback, there were still some that had hope for. So do not write off the Hubble telescope. It merely means it's not going to be quite so good as expected until the repairs are carried out. Replacing the mirror wasn't practical. So instead, Ron and the rest of the team created an instrument called CoStar, which would act almost like a pair of glasses, redirecting the light to account for the flaw in the mirror. My job was to provide an electronics interface box called the Remote Interface Unit CoStar. 3 years after Hubble's embarrassing start, they finally had the parts needed to fix the broken Hubble Space Telescope. All that was needed now was a team of astronauts, bold enough and daring enough to attempt a mission of this magnitude. There weren't very many of us in the office at that time who had done spacewalks, and so that's how I got kind of a quick turnaround from one flight to the next. You know, in all the fails, the hundreds and hundreds of fails I came up with that I had to accommodate, I did not have a line item that says NASA put wrong mirror in telescope. Catherine Thornton and Story Musgrave were two of the astronauts that were selected for the mission. And in 1993, they set off. The world held its breath as the astronauts carried out 5 back-to-back spacewalks in an attempt to bring Hubble back from the brink. The first spacewalk on Hubble did the dance when the music starts, What you going to do? Well, you got a power tool and you unbolt the thing. You undo the connection. Zip, zip, stick it in the box, hang it over there, get the new one out, slide the new one in. It's fingertips, baby, fingertips. That's what's so awesome about Hubble. It's almost like plug and play. We installed CoStar. We installed a co-processor on the computer to give it more memory, added a new magnetometer, and other cats and dogs, as we called it. It is easy. You've got to make it easy around the world. Astronomers anxiously awaited the first pictures from Hubble new camera on the 18th of December, 1993. The results came. Applause. In right there did it. When an image hit the monitor, everyone screamed, "It just got, it's fixed." Okay, that is better than any decomposition. Those are actually stars. I think you got it. Yep, sir, a little premature, but I'll shake your hand. When the images first came back, and I saw them, made me feel proud that I was part of that mission and that we had brought the telescope back to what it was supposed to be. As a matter of fact, my understanding is the images were clearer than what they had ever expected. To the relief of Ron NASA and the entire world, Hubble was finally fixed, and it immediately began to deliver on its original promise, allowing us to see the universe in ways we could previously only dream about. Hubble was only supposed to last 15 years. Instead, it continued to make groundbreaking discoveries for more than 30. But then, in 2021, it suddenly shut down, and the team at NASA once again had to fight for Hubble's survival. So, the summer 2021 event was a pretty intense anomaly, probably one of the more dramatic ones that we've had, and Zinga is the anomaly response manager for Hubble, and it was her job to figure out why Hubble's computer had shut down and ultimately find a way to get it back up and running. But that was far easier said than done. So Zinga had to think outside the box after the first few days, and it wasn't immediately apparent that we could get a path forward to resume science. We knew we'd have to pull in a lot more folks, with Hubble still showing no signs of life. And Zinga knew she needed some very niche expertise to try and help fix Hubble. So she called upon Hubble's original architects to come back and get stuck in. When I received the call, I was honored that they would think of me to try and help them resolve this. Anytime you work on a system like this, it's part of you. It's if there's ever a problem with a spacecraft in orbit, everyone jumps in and works on it. Even if you're retired, a lot of people were concerned that we would not be able to fix the Hubble. It was very stressful. The last thing I wanted was to have the system that I spent 18 years of my life on to be the cause of the end of the mission. And so I was under a lot of stress, but undeterred by the challenge, the team set to work to identify what went wrong and get HBL back online. The telescope was down for approximately 4 weeks. I think the first couple of weeks was probably the most frustrating and the most anxiety-producing. We put together what's known as a fishbone diagram. Everything that could possibly cause the problem was written down, and we eliminated them one by one until we zeroed in on the exact cause. It was amazing how everything came back to me on July 15th. Nzinga and her team successfully powered up the backup computer on board Hubble. And over the next few days, the team gradually brought the science instruments back online once we realized that we had solved the problem and the telescope was back up and running. It was quite a relief. Mainly relief, a lot of relief. How did it feel compared to 93? In my case, it was even better. This was my system that had stopped, that had halted the telescope, and to be able to get it back up and running was very proud. I was very proud when, after the first servicing mission, that we got the telescope up. It was about to be announced in a minute, and I could actually feel it. I felt it land, but the harpoon didn't anchor it, and the little crampons on the legs couldn't get a grip, so it bounced, and we had no idea what was happening, where we would jump, how we would land, or when we would land. Oh dear. Philae had crashed off the face of the comet and bounced about 1 kilometer back into space. Any further, and it risked escaping the comet's weak gravitational pull and drifting off forever. Anxiously, we waited. We had no idea whether this would be a successful mission or just a touch and go, where we would never hear from the lander again. Then the news came. We did land somewhere, and we still had radio contact. This was the moment of great relief, the moment we knew we were on the surface and could still communicate with the lander. But the good news didn't last long. It had landed in the shade, not ideal for something reliant on solar power. This meant less than 72 hours of battery life to carry out months' worth of scientific collection. The clock was ticking. It was one of those moments where you think, okay, let's throw away 10 years of calculations and redo everything in 5 hours, which is exactly what they did. The sequence was optimized to get the maximum science out of the energy available. Even with just 70 hours, the team knew they had to act fast, and turning off instruments wouldn't help. The battery had to keep heaters running to maintain the instruments in the freezing temperatures. So, 70 hours was it. They barreled through, getting as much data as possible. Amazingly, almost all of Philae's instruments survived the impact. It was go time. We were lucky. Its orientation allowed the antennas to point upward, enabling a radio link with the main spacecraft. The instruments could be switched on, and fantastic science was done. Around 80% of the science goals were achieved. It was an incredible success. Even a crash landing couldn't stop it. Watching the battery voltage drop and knowing Philae would go into hibernation was sad. But in those few hours, Philae revealed a world full of surprises. Dust, debris, and gases erupting from deep within the comet. Even the bounce itself provided insight into the surface, which was harder than expected. Perhaps the most exciting discovery was what the comet taught us about ourselves. Rosetta's mission aimed to understand the building blocks of life. Comet 67P was rich in organic compounds, phosphorus, carbon, oxygen, nitrogen, and the amino acid glycine, all essential for life's origins and hinting at how these compounds may have arrived on Earth. While Philae went into eternal hibernation, Rosetta continued orbiting the comet for 2 more years, collecting data. Eventually, Rosetta's time also came. In a final effort, the team crash-landed it on the comet, gathering data along the way. The cameras captured the surface rushing up to meet Rosetta until the signal died, a small, silent goodbye. It was devastating. People cried. I cried. It's a robot, but it had been part of our lives for so long. That was the end of the Rosetta mission. Even now, countless publications use its data. Rosetta transformed our understanding of comets, the evolution of the solar system, and the formation of life. It's rare in a lifetime to be part of such a project.